Diffusion samplers are a technology that entered the environmental area about 10 or 15 years ago. And there are a couple of different styles. This is one that is used in water wells. It consists of a polyethylene bag that's put into a protective case here and lowered down in the well. And another variation is shown here. It's a bottle that is covered with a polyethylene membrane here. The cap is screwed on. And then in these two cases, the compounds that are in the water diffuse through the polyethylene and accumulate inside of the bag. And then you pull the sampler out and you take a sample of the fluid inside, either the water or in this case the gas, and you analyze it. This is a version that is designed to sample air. The collector is right here, and compounds in the air diffuse up through this tube and are collected here. So, what we want to do is analyze the diffusion of compounds from a water bath, or from water that this thing is immersed in, through the polyethylene layer, and then the accumulation inside the water and on the inside. And the question would be, how long do we need to put this thing in the well or in the water body? Here it's being used in a lake, before it equilibrates. And so I set up a model that is designed to answer this question by representing the diffusion sampler geometry shown here. So this is an axially symmetric model. So this is the sampler here, and it'll be revolved around this vertical axis. And the geometry is built as a rectangle, one rectangle here, and then these quarter circles on the top and the bottom. And then all of that thing, this is the sampler here, and that's embedded in this material outside, which is also a larger rectangle, that is the water that it's immersed in. So let's take a look at the whole thing like that. Okay, so that's the geometry. And one of the things that I did here that we haven't seen before, if I go up to definitions, as I set this model up, I'm going to want to use this thing right here, these three geometries that represent the sampler. I'm going to want to use that several times. And so what I did was to right click here, and I included a selection that is this kind, an explicit selection, and I get this. And then I went and selected these three domains, and they're selected there. And I changed the name to sampler. And now when I go and select domains, I can automatically go to the domain that's called sampler and select, and I'll get these three domains, and it will be these three domains here. So it just is a way of identifying a more complicated set of domains by a single name, and then I can refer to them in a consistent way as I build the model. So while we're up here in definitions, I've got two of these kinds of integrals. So this is an integration over the sampler, and this is the average over the sampler. And you can see in this case what I did was to put in this function, and then when I had to specify the selection, I just went right here to sampler, and I automatically got those domains. Okay, so under the physics, it's transport of dilute species, and let's take a look at this. The initial values on the outside here, this is the water on the outside, and so we're going to give it a concentration of 1, and the initial values on the inside, a concentration of 0. And here I've used the selection to specify this domain. Okay, so now this one, the thin diffusion barrier, this is selected right there, and this is basically the type 3 or a Cauchy type of boundary, and it's set up in this case to be used as an internal boundary. So I specify it here, and I go and select these internal edges. And what it does is it allows me to define this as a thin layer and diffusion occurs across this layer. But the advantage is that I can define it just simply as an edge, and I don't have to actually explicitly make it a layer in the model. You know, if I wanted to do that, this polyethylene is only about a tenth of a millimeter thick, and so if I wanted to make it explicitly a thin layer, then I would have to go in there and have another line that was very close to this one that defined this as a layer, and that would just be tedious. It would be inefficient in the meshing, and so this is just a much simpler way to include that thin layer. Okay, so I specified it, and then here are the equations that define it. And this is just saying that the diffusion normal to the layer is going to be proportional to the diffusivity of the layer divided by the layer thickness and the concentration difference across the layer. So we have to specify the thickness of the layer here and the diffusion coefficient. So this diffusion coefficient, this will depend on the material that the layer is made out of, and also the compounds that are diffusing through it. And I came up with this diffusion coefficient by I looked it up in a paper that is where people studied the diffusion of organic molecules through polyethylene. That paper is attached, and you should check it out to select the correct diffusion coefficient for the problem. Okay, so here's the boundary conditions. The external boundary here will just stay is specified as a concentration of 1. So the initial conditions in this internal region are that the concentration is 1, and then this boundary condition here specifies it as 1. So we'll hold the concentration fixed right here. And then we have this thing here, which is just allowing me to change the diffusion constant. And what I did was the only change I made here was for this region, the water outside of the sampler, I made the diffusion coefficient 1 times 10 to the minus 8, whereas inside of the sampler right here, it's 1 times 10 to the minus 9. And so my thinking here is that this is a water body. There's some movement, perhaps some flow that is going to be mixing the water a little bit more than certainly in this bag, and so I'm just going to include that mixing in this diffusion constant, and just basically the diffusion here in this material is going to be a little bit faster than it is inside the bag. We could try this with try it as 10 to the minus 9 and see what kind of sensitivity it has, but that's how I set this up for this initial run. So for the mesh, I meshed these two different regions, the sampler and the region outside, with two different settings. The sampler here I'm specifying is meshed more finely than it is outside, and that's the resulting mesh that I'm using for the problem. And then I ran the study for a representative time here, and let's take a look at the results. So here's the results after 10 to the 5th seconds, so a little bit more than a day. And actually, let's scroll it back to the first results. So here, this is 10,000 seconds, so like 3 hours after we've put it in. And what we see is that the blue is the zero concentration. So most of the water is still at zero concentration. There's a little thin layer here that's starting to change composition, and also the water outside of the sampler is starting to, the concentration is being reduced. And so if we go out a little bit more, this starts to evolve. The concentration, the mass diffuses in, and we can see the lighter color red as, I mean, basically what's happening is the mass on the outside of the sampler is diffusing in and causing the concentration to increase on the inside. And as that happens, the concentration right on the outside of the sampler is being depleted, so the concentration out here is dropping. And you can see that light color red is right down here about 0.85. Okay, so this continues on, and you see it progressing with time, and slowly the core of the region here is, I mean, right now it's still, well, I guess it's rescaled, so the core has been affected at this point, and it's at a concentration of 0.3, but still well below the outside. And this progresses with time. We can take a look at how this happens when we look at the player and look at it happening with the slider. So it's equilibrating here, and after this time, we're probably about 80% of the external concentration, and then finally here towards the end, we get pretty close to the external concentration. And so we can see how this progression of concentration works with time a little bit more clearly if we go and take a look at, say, the average concentration. So what I do is go here to derive values and put in this global evaluation. And so I did that, and I specified this function here, sampler average, which is this function that I created there. That's the average over the sampler region. And I specified C, so I'm taking the average concentration over the sampler. And then if I evaluate this, I go down here for the results. I'm going to X that out, just clear all this stuff out that I've done before, and so I'll reevaluate it now, and here's what we get. So we have concentration, the average concentration now as a function of time, and those are for all the time steps. We can plot it, and we get that result. The plot that we're seeing here is generated here, and we can edit that in the same way that we've edited plots in the past. We can see the average concentration increasing and approaching 1 after this much time. We can get the specific values of time if we're interested. If we want to scroll down here, these are the numerical values. So if we're interested in 95% of the outside concentration, that occurs 5e to the 5 seconds. 99 is a little bit longer. It's right there. Transition from 0.98 to 0.99. So we can get numerical values out of it right here. We might be interested in some other things. Let's see. Radial profiles. I set up a cut line here that is a profile through the sampler at this height, and we can plot that up right there at different times. So after 10,000 seconds, we see a thin layer here where the concentrations are starting to change in the sampler and outside of the sampler. After 3 times 10 to the 5th, we've got a profile like that, and 10 times 10 to the 5th, we see that the concentrations inside the sampler look like they're pretty close to concentrations outside the sampler. So looks like we're able to get a pretty good estimate of how long it would take for this sampler to equilibrate. Now, of course, it depends on what the thickness of the layer is, the thickness of the polyethylene, as well as the diffusion constant. And those things may change depending upon what kind of well, the thickness of polyethylene varies depending on how it's manufactured, and the diffusion constant will vary depending on what compound you're interested in analyzing, what's going to be diffusing through the layer. So those may give you somewhat different results. So something else I'd like to point out, in this case, we may be interested in measuring what the volume of the sampler is. And since the geometry is fairly simple, we could calculate what it is. But in other cases, it won't be quite so easy to calculate what the volume is. And so we can use these post-processing integrations to get what the volume is. And actually the volume may be changing. We may want to measure it on the fly for some application. So let me just show you how that works. I went here to derive values and inserted the integration here, and I picked a surface integration. So I got that, and I selected here this thing, the surface that represents the sampler. And I've used this kind of thing in the past and put like the concentration in here as the integrand. But if I just put in 1, then what happens is this is the integrand, and it integrates this over the area of that we specify. So it gives us the result, if we don't do anything, will be the area, the surface area. But because this is an axially symmetric model, we can also use this to get the volume, assuming that it's revolved around the axis. And we do that by checking right here. This is available for the axially symmetric models. And so doing that and using evaluate gives us the volume right there. And in this case, I specified for the time selection just this one time, because in our case it's not changing, and we would just have a long list of the same values. But if it were to change, then we would see that change here. Okay, so that's something that can be done either in post-processing, or you can do the same kind of thing up here, set up a definition that measures the volume of some entity in this way.